Okay, very good. Okay, everyone, welcome to the final installment of 4820 for this semester. Me and Stefan will be giving this last lecture um, jointly. Um, it will be the first part of it will be sort of a very high-level round of just summing up everything we've been covering in the course. We'll try to focus on some of the overarching themes that have sort of cut through everything we've been talking about. So we'll start with a couple of slides on just very high level sort of bird's eye perspective on what we've been doing, and then we'll sort of very quickly just run through some of the sort of some main bullet points highlighting what we've been talking about throughout the lectures. And then finally, there will be some sort of just practical details regarding the final exam. There might be prizes involved as well. We'll see. And a sample exam at the end, so the one that Stefan has already posted, and hopefully most of you have already had the time to look at and try to solve. So hopefully you have some questions about that. We won't have time to go through all of it, but you'll get to sort of make requests about what problems you would like to see reviewed. Okay, so that's the plan. Okay, let's just start with the very high level view of what we've been doing. There's going to be three main points on this slide. So at the beginning of the course, we mainly dealt with what we can describe as point-wise observations. So in our case, we focused on representing words, or more precisely, the meaning of words in a vector space model. But the point is that what we were trying to represent here can be seen as sort of individual data points, single objects. Although we did also try to model groups of these different points, doing classification and so on, but we still only dealt with sort of the problem of assigning class memberships to individual objects or observations. And then, when roughly halfway through the course, we started looking at sequences instead. So sequences of events, sequences of observations, rather than just individual single data points or observations. So in our case, the sequences were strings of words. So we moved from individual words, as our example, to strings of words or sequences of words. And also when doing classification, we did sequence classification instead of point-wise classification. So here we added so it's sort of two layers here when we worked with sequences. With first the simple n-gram models, just the linear sort of observed data, and then we moved to tagging and hidden Markov models, where we added this one additional layer of the hidden states, right, that we thought of as having generated these observations. And then finally we added yet another layer of structure when we introduced in our case syntax and looked at hierarchical structure, and we sort of shifted focus again from just looking at strings of words or sequences of words to now viewing these sequences as sentences that are structured and made up of sort of constituents. And in this move, there were sort of two different aspects to what we were doing. There was one sort of declarative aspect, namely that of defining the formal grammar, defining the rules that declaratively sort of define what are valid structures. And then there was a procedural aspect in terms of the particular algorithm or parsing strategy that we used for trying to uncover this structure given a sentence. And across sort of all of these different perspectives or problems, or what you want to call them, moving from individual words to sequences of words to to structured sentences, all along we dealt with trying to automatically learn something, automatically acquire information about these observations automatically from data. So just wanted to spend one more slide on trying to sum up what was the simple common thing that all of these different sort of learning problems or classification problems shared. Let me just bring up some more points here right away. So we've worked with various sort of problems that we've approached as learning problems. So we've applied machine learners for automatically from data learn something about either class distributions or the probability of sequences of words or parse trees. But the common thing to all of these different sort of learning problems, the way we have solved them, is really that we've basically just been counting observations. It's sort of very simply put the essence that all of these different things we've been doing share. We've been counting observations, and importantly observations sort of in context. Maybe it would have been more precise to say that what we have been counting is actually the contexts, the contexts themselves. I mean, the observations have in a sense been context. So for the feature vectors, for example, just to be a bit more concrete, so for the feature vectors in our initial sort of semantic space word models, we counted different context features of the words, like bag of words features or grammatical features or n-gram features. For the linear n-gram models, the language models, we counted the n-1 previous words in the history. For the hidden Markov models, we counted the n-1 previous states in the model. For the probabilistic context-free grammars, we counted local subtrees in the trees in our training data. But the one simple thing we've been doing all along is basically just counting observations and then using that to make predictions about new observations, new data. Okay, one more very high-level slide on a recurring theme in what we've been talking about, namely data structures. We've been dealing with data structures on sort of two different layers. So on the one hand, there are the abstract data structures that we have used to sort of conceptualize the problems that we deal with. The data structures that we've used for thinking about a problem. So for example, for the task of modeling word meaning, right? Then we decided to use a vector space model for to represent our data and to sort of frame our problem. We could have chosen other sort of metaphors or framework or abstract data structures for thinking about our problem. So we chose this spatial geometrical model for representing words, but we could have decided to phrase it as probability distributions instead. So forgotten all about that whole sort of geometrical metaphor and said that we want to think about words as probability distributions over contexts and define measures instead of computing the Euclidean distance or the dot product, the cosine. We would have had measures that that compare probability distributions. So that's one kind of choice that we've made with respect to a data structure. And then there's the more low-level choice, which relates to how we have chosen to implement that particular abstract data structure. So once we had decided to use a vector space model as our sort of abstract model for representing word meaning, then we had to face the question of deciding how to implement those models in Common Lisp. If you remember, we said that the vector space model can be thought of as a matrix with rows corresponding to words and columns corresponding to the dimensions of the space. And then we went one more step and said that we could implement this sort of feature matrix a co-occurrence matrix using either lists of lists or arrays of hash tables, as we did in the sample solution, or many other different configurations of actual concrete data types in Common Lisp. And these two, so making sort of design choices on these two different sort of levels of abstraction when it comes to data structures have been something we've dealt with for all the problems we've covered throughout the course. Okay, that was it for the very high level sort of bird's eye view on things. Now will be a bit more chronological in the sense of sort of starting at with the first lectures in the lecture series, and then quickly just run through the themes we've been covering and just jointly remind ourselves about what we've been doing. Okay, so we started out with this crash course on Common Lisp, right? Some of the important concepts that we spent some time on in class were things like higher order functions. So this concept that functions are data types that we can use just like any other data type in the language, and that means that we can pass them as parameter values to functions, or have functions themselves return functions. We spent quite some time talking about recursion, different ways of writing recursion, so ordinary recursion or what we call tail recursion, and comparing that to constructs like loop or do list, so special constructs for doing iteration. And of course data structures, which I also talked about in the previous slide. So data structures is, I guess, the sort of part about the implementation language that has popped up every now and then in the lectures, also after these two first dedicated Common Lisp lectures. But for the actual exam, we won't actually sort of give you questions that have to do with sort of the particularities of Common Lisp syntax. Obviously, that's not the important thing here. We might ask you to write simple functions to just show that you master sort of central concepts, or to ask you to, for example, like we just now did, jointly reflect on what choice of data structures are appropriate for representing a given problem, for example. Okay, then we turn to talk about vector space models. So this very general framework for representing basically arbitrary data. We could use it to represent more or less everything. So I think in the first lecture when we introduced vector space models, we introduced it with the example of representing physical traits of people, right? And that we could have properties describing things like height or hair color and things like that, and assign those to dimensions in the space. And then people would be positioned as points in the space according to the scores they would have relative to these different properties that we measure. In the Manning-Ragavan-Schütze textbook, they use vector space models for representing documents. And these models can and are used to represent basically any type of data you can think of, be that sort of images. To do image recognition, for example, we could have a digitized image consists of pixels. We could think of each pixel as corresponding to one dimension in our vector, and we could have the values in the vector reflect the shade or the color in that pixel, for example, and we would have a representation that we could use for image recognition. So it's a very flexible general framework, and we happen to use it for representing word meaning. And in that context, these models are typically called semantic spaces. And our starting point here was this thing we call the distributional hypothesis. This idea that the meaning of a word, the semantics of a word, can be characterized by its pattern of use as extracted from data. So that means that we can, so comparing meaning then reduces to comparing context patterns. And context patterns in this context is implemented as computing geometrical distance in the model. We looked at different ways of defining context, different ways to do normalization, like lemmatization, stemming, and so on, different distance metrics that can be used, the importance of length normalization, and the effect that that have on reducing frequency bias and even speeding up some of the vector computations. And we spent quite a bit of time dealing with this property of sparsity in the vectors, right? The fact that very few features in these feature vectors for our words were actually active or had a non-zero value. And this is one point where we sort of return to this issue of choosing an appropriate low-level data structure. Okay, and then while we were still working in the context of vector space model, we turned to two different categorization tasks where we applied two different sort of main approaches to machine learning. So one was classification as an example of what we call supervised learning, and cluster analysis as an example of what we call unsupervised learning. And so in supervised learning, the idea is that we have labeled training data. It's supervised in the sense that we have a guide in terms of what it is we're trying to learn. Whereas in unsupervised learning, we have no label data, and we're left with only the data, and in our case, in cluster analysis, whatever similarity measure we chose to define or chose to sort of impose on our data objects. Some of the issues common to both classification and cluster analysis that we talked about was different ways of measuring similarity, different ways of representing classes, and different ways of representing class membership. We return to some of these points. So for examples of classifiers, we looked at Rocchio classification or nearest centroid classification, and K nearest neighbor classification. And some of the differences between these have to do exactly with how to represent classes, right? So the Rocchio classifier represents classes using these abstract prototype vectors that we call centroids, these average vectors. While in KNN, there's really no class representation at all. We just store all the examples that we've been given of a given class. And we spent quite some time talking about different assumptions that the different classifiers implicitly make about our data. So Rocchio, for example, can only deal with linearly separable classes, whereas KNN did not have that constraint. And we talked about how Rocchio implicitly assumes that the classes are so the regions that the class form in the space roughly corresponds to a sphere of equal radius, right? And that we could get problems if the actual distribution of the data did not fulfill that assumption. Basically, if the class distribution was actually sort of stretched out in the space, or form disconnected, non-contiguous regions in the space, and so on. Another difference that we spent some time on was where we have the complexity for these two different methods. So with Rocchio, none of them are very complex. They're both fairly simple, but still, when comparing these two, Rocchio spends most of its computation in the training phase, computing these centroids, whereas KNN actually does no training at all. It basically just stores all the examples, and all the complexity goes into actual prediction to the phase when we actually apply the model and perform classification. Finally, when we talked about classification, we discussed various issues related to evaluation, how to evaluate models, different scores we could use, such as accuracy and precision, and so on, and these notions of false positives and true negatives and so on, that we use for defining these different scores. And we looked at sort of different trade-offs between some of these different scores and what problems they might have in different contexts. And we also spent some time on talking about how to compute these scores in the face of having multiple classes, so in doing multi-class classification. Okay, and then we turn to this second categorization task, namely clustering, unsupervised learning, where we discuss two sort of main families of clustering methods: the hierarchical methods and the flat methods, with k-means being our main example of a flat clustering method. Don't think I'll need to spend time on sort of going through all the bullet points here. I think it's better left to you to read through and repeat for yourself, make sure that sort of all of these highlighted points mean something to you, and that you have something to say about all of them. And the other main sort of family of clustering methods that we looked at was hierarchical clustering, where we spent most of our time talking about bottom-up clustering, or agglomerative clustering. And how we then bottom-up build this structure that we visualized as a dendrogram, where we have that shows sort of when the different clusters have been merged and what similarity the different clusters had at the time of merging. And we discussed these different so-called linkage criterions, these similarity measures that compute the similarity between groups of objects, between clusters of objects. So single link, complete link, centroid, and average linkage were the four we looked at. Then we just briefly mentioned divisive clustering, which is sort of the top-down variant of hierarchical clustering, which is performed by repeatedly applying a flat clustering method, so building this tree structure top-down. And this was roughly where we were at in the lecture series when Stefan took over. He'll take over now as well. I hope he was nice to you. And that you were nice to Stefan while I was away.
I can leave for a minute and then they can answer the first question.
Do you want this one? Or?
I thought it would be fun to have two microphones. Yes, I'll take it. You can see whether you get this one. All right. So I'll similarly try to give a high-level summary connecting the dots from the second half of the term, and the main change was maybe that I started to lecture instead of Eric, and we switched from a geometric vector space view to a probabilistic view, where what we did repeatedly is model probabilities of various elements, words or labels, which could be parts of speech or constituent labels in particular configurations, and used these probability distributions, these models, for different purposes. And the sort of main organizing thread of increasing complexity was we started with sequential or linear structures and then moved to hierarchical tree structured structures. This you've seen many times. talking about the probabilities of strings, and I think I would like to think I've given you a good idea of the many applications where that is useful, where we use it in interacting with internet technologies or our cell phones every day. The sequence labeling task, assigning labels to the elements of an observable sequence, in our application to natural language, the parts of speech, the morphosyntactic lexical categories of individual tokens. The Viterbi algorithm is widely used outside of natural language processing in bioinformatics, but also in error correction, in various data communication protocols. So also there I would like to believe that you see the relevance of the model and the algorithm beyond its application to natural languages. Maybe most specialized to natural languages and the pervasive problem of ambiguity in natural languages, parsing hierarchical models, where we said we want to talk about the probabilities of the two different interpretations here in terms of different syntactic structures that give rise to these interpretations. And as I sat down today, I felt, okay, I actually haven't given you enough sort of outlook of the utility of parsing. I remember I promised once and then I didn't deliver on that promise. And I don't have slides for that today, but it occurred to me it's certainly fair to say that Google today is one of the biggest users of parsing technologies that we know of. Microsoft started to put parsers in front of millions of users earlier. Can you guess in which product? The Office suite in grammar checking. So I remember I had a friend who moved to Redmond to work on the German grammar checker. I said it's kind of fun to put my technology out there and know there will be millions of users. It's also scary. So in giving feedback on grammar as you write in Word, of course, you need to consider the rules of the language. That was an early mass market application of parsing. Today, Google parses most of what they crawl from the web for more than a dozen languages, for all we know, certainly everything they crawl for English. And they use these structures in several of their products, certainly in machine translation. So machine translation is no longer purely string to string. They actually model on the target language side syntactic structures, so it's string to tree. They also use them in constructing the knowledge graph and linking, so the knowledge graph, this giant world knowledge model that they're constructing, and to try and link relations in running text to concepts in the knowledge graph. In, what is it called, Google Now, Android's Siri, where you talk to your cell phone, how do they work out what you're asking the machine to do? The first thing they do is they consider syntactic structure. So in a growing number of products, mass products that try to make sense in some notion of sense, or understand in some interpretation of understand, natural language, syntactic analysis is increasingly the necessary first step towards interpretation. It happens behind the scenes, we don't see it, but it's certainly there. Okay, now let me move on, because we also want to leave time to actually talk about the exam. I suspect you might be interested in that too. I'm sure you're here today to hear us sum everything up, but let's try to leave some time for the exam. So this linear hierarchical mode of organization will be on the next 2 or 3 slides. We had n-gram language models talking about probabilities of strings, and we model the joint probability of W1 to Wn as the product of conditional probabilities. And we apply the Markov assumption, limited context, to make that work in practice, to actually be able to estimate probabilities and to execute that computation. In the part of speech tagging or the sequence labeling task, we add a hidden layer of abstraction for natural language parts of speech, which we cannot observe. And again, we use the chain rule and the same Markov assumption on the state sequence, the hidden layer, and link it to the observation layer through, so we have the transition probabilities and the emission probabilities that link the hidden layer to the observations. And in parsing with context-free grammars or probabilistic context-free grammars, the hidden layer, again, something that an abstraction that we cannot see, are the trees, the syntactic analyses, the syntactic structures. And here we have the same application of the chain rule over sub-events. So we model the joint probability of all of the subtrees in the tree as the product of conditional probabilities. I'll flesh that out. And in the linear models, we have the Markov assumption. These are Markov chains, Markov chain models. Also in the PCFG modeling approach, we have a strong independence assumption because we assume that the context-free grammar assumes that in any context where an NP is called for, I can use any of the rules, that is any of the subtrees rooted in NP that the grammar can generate for me. That is also a very strong independence assumption, just like the Markov assumption. All right. All of these are arguably instances of supervised machine learning. Eric defined that as estimating the model parameters from labeled data. Now for the n-gram language models, you could argue there are no labels. So would you call that unsupervised learning? It's, yeah, I couldn't quite make up my mind. So we train that on raw text. There's no need, there's no hidden layer, and hence there's no need for manual annotation. But in all cases, we instantiate the same template to estimate the individual probabilities. And they all come down to counting the size of the event set and normalizing it to the size of the conditioning context. So for an n-gram, let's assume n is 2, then this is counting bigrams and this is counting the unigram prefixes in which the bigrams occur. You've seen this many times. And the exact same pattern applies to the HMM, transition and emission probabilities, and the rule probabilities that we attach to the productions of the PCFG. Here the conditioning context is the left-hand side symbol, the non-terminal that the rule rewrites. These were the models, and then we put, or we combined these models with algorithms to compute in this probabilistic space. And computing the probability of a string using a language model is a straightforward application of the chain rule. HMMs, we studied 2 tasks, actually using the HMM as a language model. That is to assign a probability to a string as the sum of probabilities for all possible state sequences emitting that string. But maybe more commonly, to find the most likely state sequence, to actually determine the most likely, the most probable sequence of states, sequence of parts of speech on the hidden layer for a given observation sequence. The CFG, without probabilities, gives us this notion of a formal language, the strings recognized by the grammar. And adding probabilities, I can now disambiguate. I will often have multiple grammatical structures for a given string. And I can then decode, that is, extract the highest probability tree from the packed structure constructed by the parser. And here we have the main applications of dynamic programming. Again, sort of a different perspective on these 3 problems that we have solved, and trying to identify the commonality. And obviously, we apply dynamic programming in all cases, which decompose into recursive subproblems to make computation tractable. And these problems are amenable to dynamic programming because they can be recursively decomposed. And in the HMM, we introduced these V of IX, I think we called them, the Viterbi matrix and the forward matrix to cache, to record the intermediate solutions. In the parsing world, the intermediate solutions essentially are edges, passive or edges, active edges, and they organize themselves naturally in the parse chart. And the parse chart filled with edges for a given string is what we call the forest. And then over that forest we can apply the Viterbi algorithm adapted to hierarchical structures to extract the highest probability actual tree from the forest. In all of these problems, we need to say how we judge success. That's the problem of evaluation. For part-of-speech tagging, we use the dominant metric tag accuracy. For PCFG parsing, we looked at two metrics: coverage, how well does the grammar actually cover the actual language. A grammar may undergenerate. We saw that in the parsers that you just constructed, we actually did not have perfect coverage, as I had led you to expect 2 weeks ago in the previous lecture. A typical PTB parser will accept pretty much any string, but a typical PTB parser also has a mechanism to handle unknown words. Our parsers don't have that mechanism. So as soon as there's a number or a name that we haven't seen in training, our parser just cannot do anything because it cannot even initialize that chart cell. And that's why we have partial coverage in our parser implementations. To judge quality, we looked at the parseval metric, which breaks down parse trees into labeled, into constituent labels or labeled bracketings, and thus produces or yields a granular evaluation metric. We can talk about partial correctness. It's not that the tree is just right, perfect, or it's completely useless. We can talk about precision recall and F1 scores at this level of the individual labeled constituents. All right, so that was our attempt at putting things into perspective. So there was a coherent theme to our course design, even though you may not have seen it at all times. We hope you see it now. And now let's sort of move towards what must be on your minds these days, exam preparations. This is what we consider relevant reading for the exam. So it's fair game to ask you about things that were on the slides. We have screencasts from the 3rd week, I think, and the selected sections and chapters from the various books that we assigned on the course schedule. And we also assume that the model solutions that we have published and discussed in the group meeting, you find these in SVN. Model solution for 3B is also out now. That you have some understanding of how we actually solved these problems, or what an adequate solution of the problems that the assignments that we gave you was. The actual exam is at 2:30 on December 7. It lasts for 4 hours. We're asked to think, so it used to be that exams were 3 hours, and 3 years or so I think they were extended to 4 hours. And at the time we were told to still sort of assume that we should design an exam for 3 hours. So we'll try to make it so that you should have enough time. So time, but I mean, it still makes sense to read through everything and sort of not waste your time. There will be close to 50 people taking the exam. I can't guess in which location you'll be sitting, but I'll be the one who comes around roughly half an hour into the exam to see whether our exam text is clear and makes sense to you. So I'll see you one more time on December 7. Excuse me. Because we're teaching in English, the exam will be in English, but you're of course free to answer in either English or any variant of Norwegian that we can make sense of. More is more. How do you mean that? I think less is more. Maybe was what I had last year. This is a tricky question. So sometimes people sort of feel that it can be a good strategy to just dump everything that you happen to remember when it seems vaguely related to the question. That is not a good strategy. That wastes your time, it wastes our time. It doesn't necessarily lead to happy reviewers. So as long as it's relevant, I think is the key phrase here. You've had some practice taking exams. High recall and precision, I think, is a great balancing act to recommend. Spell out what you think. Be specific. An exam is not the time to be modest, not even in Norway. So when you feel you recall something clever or think of something clever, share it with us. The exam will have between 4 and 6 questions, and they account for 100% of the total, and each question will tell you what percentage of the total it makes up. So you might want to start on the the easiest question or those that have the largest point number. You should be able to pick your strategy. All right, we would strongly like to encourage you to participate in the course evaluation operated by the student union, student representation at the department. You might feel that you've given some of these comments already in our halfway questionnaire, but that was to us, and also there's more substance to the final course evaluation. You also have a much better understanding of the course now. I have to honestly recommend that you do that just right after the exam, because then you're really in a good position to have an opinion on your course experience. You might be angry at us, but still, I think that is the most constructive time. So even if you're angry at us after the exam, I hope not, then say, okay, now I can tell them and go to the link that you have received for the course evaluation. If we've helped you realize that language technology is very fashionable and a thing of the future, then there is one more course that you can take as part of your master's studies if you haven't taken it already. Search Technology by Alexander Örn, coming up this spring. Overlaps in part even with the reading that we have used. Introduction to Information Retrieval. And runs as Inf 4800 as a master's course. Well, I can't say what I was going to say. There's a missing slide. It was commented out until right before the lecture. Sorry about this. it is. Please. Coming right off. Yeah, I can. Ha! There's the extra slide. So before we take the break and then actually talk about the exam, just to give you, yes, here it is. I can see it. There it is. Some statistics of how we went through the semester. There were 61 of you who submitted for problem set 1. That's an all-time high. And down to 46 now for the final problem set. And that's actually a fairly respectable retainment rate in our experience. Probably, I should say. 44 or 45 qualify for the final exam. And we expect to post preliminary, so some of you have seen your feedback already. I think Siva has done his grading. Mohav is grading as we speak, and he'll post preliminary feedback in the course of the day still today. So by the end of the day, you'll know whether you have qualified for the exam. And the sort of full-blown feedback he'll fill in the next couple of days on 3B. Obviously, there is, as there should be, some spread between just qualifying or bringing home almost all of the points that one could collect throughout the term. The latter is an attitude that we sometimes seek to stimulate. I think we didn't say so explicitly this time, but that's really what we would like you to do. To not just try to qualify, but to try to do full score whenever possible. And so there are 2 of you who actually collected 52 or 54 points of 58, and that is, I think, we think, fairly impressive. And hence we thought we'd name those 2, the winners, and see whether they're here, are Ole Jørgen and Elena. Elena is not here today. That's a shame. And Ole Jørgen, that's you. Okay, because we have a little prize, a token of pride for Inf 4820 assignment high score, something that you can wear with pride to the Christmas party or the exam. Congratulations to all of you. Do you have one already? Good. nor does Elena. So that's really at our department. Not many people get to wear these T-shirts. So speaking of which, December 1 is the deadline to pick master level supervisors. Do you have a project already? Well, come talk to us. We still have supervisory capacity, all of you. So if you might be interested in a master's project in the language technology space, then we'd be very happy for you to make contact with us. That's everything before we actually talk about the exam. I'd suggest we take a 10-minute break. Is that acceptable? And be back here 17 past, and then actually look through our sample exam with you.